to us on the early stages of planet formation. We now have some of you may not yet be aware, Chris Thompson has become interested in planetary topics. Because if you didn't know it yet, it will be abundantly clear in a few moments.
So Andrew is my wise counselor in things planetary. Could I use the previous? Hopelessly inadequate. The basic thesis of this talk is that outflows are a generic part of planetesimal formation. So what I'm going to focus on is the interaction between what one might view as steps 2 and steps 3 of the process of building up planets. So dust will already have been assumed to have accumulated into particles, which couple only marginally to the gas. And we will also assume that gravitational stability has taken place, and we will focus on the material that's left over at the end of this process, or the outer part of a collapsing cloud of particles. And the whole question really revolves around how is the energy of gravity, released by gravitational stability, radiated away. So we're interested in a case where gas is still present, the sound speed is assumed to be higher than the escape speed from the planet, so that we're dealing with a radius less than 1,000 kilometers or so. Loading of gas near the planetesimal by dust can reduce the effective sound speed so that the two-component medium, dust plus gas, can become gravitationally bound. And let's start off with a very simple toy problem. I have a point mass essentially moving through a uniform medium of gas and particles. Well, the mass has a finite dynamical time at its outer boundary, and we'll be interested in a case where it's moving at less than its escape speed. And one recalls that in this case, the cross-section for an ambient particle, the absence of gas to be deflected by a significant angle, goes as the geometrical cross-section times b planet over the escape -4, and the accretion cross-section is down by the ratio of the velocity squared. Now, in this situation, if the stopping time of the particle moving through the gas, reduced here by the gravity of the planet, is comparable to the passage time across the radius of gravitational flux of the planet, then the accretion cross-section goes up and becomes larger. So here's a simple calculation where one has the stopping time for the particles 100 times the dynamical time, and dp is 0.1 of the escape. So if this ratio of quantities is less than unity, then the cross-section is reduced basically by this factor. And if that quantity is larger than unity, then the cross-section very rapidly cuts off. So here are 3 curves for 3 different cases where the planet is moving at the escape speed at 1/3 of the escape speed, 1/10 to 1/30. So this corresponds in a disk context to the product of orbital frequency times the stopping time, larger than about 0.1 for a planet of 1,000 kilometers per minute at the escape speed. So, in the case where the stopping time is larger than the dynamical time on the surface of the planet, the particles are just spiral in. Is this a stable accretion solution? The answer is no, because the particle for a crater of 100 or 1,000 kilometers is moving very rapidly through the dust, so that a dust grain incident on the particle surface releases enough energy to eject a lot more dust grains. This is extremely important in the case where the particle is basically a dust clump, but even if it's previously incorporated in the planet to about 700 degrees or higher, and essentially fired, then it's still because the escape speed from a planetesimal of a radius of 1,000 kilometers is a kilometer a second. So the e-folding time for the dust in the vicinity of the planetesimal is very, very short. Nonetheless, this, a good part of this accreted material can become gravitationally bound to the planet if the mass accumulated is enough to reduce the effective sound speed below the escape speed in less than time for the ambient gas to flow across the planet. And so that requires fast accretion, especially if this fragmentation speed is only a meter a second. So A is the radius of this small accreted particle. So one can also check that radiation, diffusive radiative transport, is hopelessly ineffective at carrying away the accretion energy. So my initial comment about radiation is completely beside the point, and it has to be convection. So the next simple thing one can check is, well, if I have the accretion luminosity as defined by the simple model of gas-mediated accretion, and it's carried by convection, and in the outer parts of the envelope, the density, basically the density of the gas, is a well-defined convective speed. And that convective speed is larger than the motion of the planet through the gas, then the solution is inconsistent. And that's true if the ambient particle density is larger relative to the gas density than a certain factor. Okay. Well, one can then approach this problem from the opposite end. One imagines that a very, very high density of solids has built up in some mantle surrounding the planet, has perhaps a few percent of the mean density of the planet. It would be about 3 grams per cubic centimeter for silver material. Now, in this situation, where you're dealing with the binding of dust particles into clumps, the size of the clumps is limited by the fact that dust cannot stick at a speed larger than about a meter a second. So in this situation, the particles are relatively small, they collide with each other very, very frequently, many, many, many times in the dynamical time. And so if they have a space density nc and a radius ac, then the equilibrium velocity of being stirred by the gravity of the planet is like this. And the mean speed with which this ensemble of particles moves through the gas, or the gas moves through it, can be a bit larger, but it's of the order of p. And so the convective speed then is related simply to the escape speed from the planet. You'll note that the radius cancels off. And I'm also assuming, by the way, that the mean density of the solids is much, much larger than the gas density. So, given that the mass in this mantle is accreting on a time scale, say, of a year, sigma speed is a meter per second, you come up with the size of a centimeter. Now, in this situation, where the solid density averaged over volume is much, much larger than the gas density. The specific heat is completely dominated by the solids, and so even though the convective mantle is nearly isothermal, nearly adiabatic, it's also nearly isothermal. So one can straightforwardly work out the density profile in terms of the ratio of the escape speed squared to the effective sound speed squared. Now, that convective speed at some point becomes comparable to or larger than the escape speed. And at that point, the energy has to be carried away in the wind. And that sonic radius is about 100 planetary radii for something the order of 1,000 kilometers in radius. Okay. So one last issue then is what happens if I add into this ensemble some ice, some water ice. Well, here you have to take into account the fact that only at about a couple hundred degrees the water ice is sublimated. And the heat that is absorbed by sublimating it corresponds to a velocity of a couple of kilometers a second. And that's larger than the KT sublimation divided by the mean molecular weight of hydrogen, helium, pi molar mixture. So one has to take into account the effect of the ice sublimation on the entropy of the gas, which is straightforward to do, and then using basically the Clausius-Clapeyron relation for the vapor pressure of the hydrogen gas, of the water vapor, which is seems to be mixed here with the hydrogen helium gas. One can work out the density profile around the planet, and the sequence of curves is labeled by the total mass fraction in dust and ice, going from 0 up to about 90%, and equal, for the sake of argument, equal contributions from dust and ice. So when the ice mass fraction exceeds about 0.3 to 0.4 on the top few of these curves, there's a very dramatic effect on the density in the inner parts of the atmosphere due to the fact that there's a zone where the temperature remains nearly constant with radius, and the density exponentiates as the water ice is being sublimated. So you get much, much higher densities here for high ice mass fractions. And in fact, you can, for the upper two of these curves, expect that the mass of the atmosphere becomes comparable to the mass of the planet if the mass of the planet is larger than the couple of Earth masses. On the right part here, you have the optimal depth through the dust. This actually doesn't include any effects of condensation clumping. That isn't a really big effect. I think the peak optical depths here can be, a million or so. Okay, so that's just a couple of things that we've been working on and made some progress on, and made development for some of the phenomenology of, well, for example, this model suggests that when you take into account the effects of refluxing, that's very easy to make crystalline dust in the outer solar system. The drop in the optical depth here is just reflected you're starting to vaporize the SiO2. Okay.
Good. Leaving a minute short there, amazingly. So we have time for questions. I'm sure there's those ideas there. Good.
What effect does this wind have on subsequent growth of the unprecedented?
I'm not sure. In part, that's a matter of understanding the environment and exactly the geometry of the infall. But the specific energy that's released, is comparable to the internal energy can be almost comparable to the internal energy in the gas. And so you can expect these outflows to extend fairly ways up in this.
I want to make sure I understand this. You're saying that the accretional energy, force is based on the accretional energy of the growing planet. And so the planet is growing, but at the same time, and then it has a convective envelope around it. And convective velocities are becoming comparable to the escape velocities. And so some of the material that's accreting is being returned.
And then the gravitational energy is be carried off by some fraction.
Right. And so the plane's basically not heating the interior of the planet because...
Well, you're raising an interesting question. I mean, could one get effectively, high temperatures of 1500 degrees, for example, up the Congo Formation, even around objects whose
that's
fighting
the
energy
thought.
is?
I mean, heating the interior of the planet comes from accreting very big objects which vary their energy very deep.
One issue that we've raised is, at what point does that accretion process really become possible? Because you take, 10 centimeter or meter sized things and they're made of essentially dust without ever being buried in something larger. They're very rapidly disintegrating.
Yeah, okay, but so some fraction of the material that's coming in is being expelled, and it's being expelled after having been heated, and it's being expelled after having been in the atmosphere, perhaps for something like a few times the escape speed across the atmosphere.
So yeah, our next speaker is Man Lee. He's speaking to us about planetary migration. Yeah.
Well, it's good to be here. It's kind of interesting to be on this side of the room because I used to sit over there listening to lectures as undergrad. And actually, that's the time when I had my first connection with CITA was in the, I guess, very early days of CITA when I probably was one of the first undergraduate working with people at CITA. So at that time, it was with Jeff Bishop and Martin Benton. So the topic I want to talk about today, so the person primarily responsible for most of the work I'll describe is Doug McNeil, who is also an undergraduate alumni from here. So he's now a postdoc working with me. So just to remind everyone what obliquities are, so it's basically the angle between the spin axis and the orbit normal of the planets. And for the giant planets, so Jupiter is 3 degrees, Saturn is 27. Uranus is kind of sideways, 98 degrees, and Neptune is about 30 degrees. Okay, so for the smaller giant planets, Uranus and Neptune, they are, well, they're at least small enough that it's plausible that you can actually produce their obliquities by giant impacts. Although it's kind of hard for Uranus, but at least energetically and angular momentum-wise it's plausible. That problem becomes a lot more problematic for Saturn because of its large mass and then spin angular momentum, and it's mostly gas, so they created most of the angular momentum from the gas, so it should probably start with a spin that's up perpendicular to the orbit plane. So giant impact would be, you need a pretty giant, really giant impact to actually produce the 26 degrees obliquity. So there's been a couple of other alternative ideas. One was proposed by Scott, and it's basically if you can twist the total angular momentum vector of the solar system on a time scale of about 500,000 years, then you might be able to produce the sort of obliquities you see in the outer solar system. And half a million year is because that's the spin precession timescale of Jupiter. So Jupiter will be able to follow it, but nobody else will be able to. But then around 2004, Bill Warren and Doug Hamilton, they pointed out a very interesting observation that if you look at Saturn's spin axis precession rate, it's about the same as one of the nodal regression rate of Neptune's orbit, or more specifically, one of the eigenfrequency G18 in the secular evolution problem for the orbital dynamics. And also that the 27-degree obliquity of Saturn's spin axis is very close to what's called the Cassini state 2 of the spin orbit, secular spin orbit resonance. I'll explain to you what the Cassini state 2 is. So their idea was that that the tilt of Saturn's spin could be caused by a secular resonant interaction, and the capture into the Cassini state. The Cassini state actually increases in obliquity when you decrease G18, the absolute value of G18. And so if it's captured into that state and there's a change in G18, then you could actually tilt Saturn, the spin of Saturn. And they also later, Bill Warren and Robin Kendall also later pointed out that Jupiter's spin may also be in that situation because there's also close approximate equality between the secular spin orbit, between Jupiter's spin precession rate and the nodal regression rate of Uranus orbit, or again, more specifically, the G17 secular frequency. So what is the Cassini state? So if you look at a simple problem where you have, so K is the normal to invariable plane, so that's an inertial frame, that's the non-rotating direction. And you have an orbit with the orbit normal n precessing at some frequency g around the invariable around k. And the Cassini states are the states where s, the spin axis direction, is in fact co-precessing with n. And there are 4 possible locations, so-called Cassini states 1 to 4. And the most relevant one for us is state 2. Okay, so when you plot, so this is a plot of the ratio alpha, the spin precession frequency, over the orbital precession frequency. And so if you start on the left-hand side, when the obliquity is small, then you could be in Cassini state 2. And as g, the absolute value of g decreases, you go this to the right. And so if you stay with the Cassini state, then your obliquity will automatically tilt over. Right? And so the requirement, so if you have any process that decrease the absolute value of g, and the most obvious ones are due to if you have a depletion of planetesimal disk, or outward migration of Neptune, that would naturally produce a decrease in g. Right? And the trick is also that you need that decrease on the timescale long enough compared to the libration timescale going around the Cassini state, so that as the Cassini changes, you can actually follow the Cassini state. Okay, so the context that I'll talk about this is in terms of the so-called Mies model for giant planet migration. So this was something proposed by Saganas, Gomez, Davison, and Borgadelli back in 2005, where they suggested that the original solar system, outer solar system, is much more compact. So the outermost ice giant is within 20 AU from the sun, and then there's migration driven by planetesimal. Where primarily, so Jupiter moves slightly inward, and Saturn, Uranus, and Neptune move outward. And the key is that at some point when Jupiter and Saturn cross the 2-to-1 resonance, Saturn's eccentricity is kicked up, which destabilizes the whole outer solar system. And then Uranus and Neptune, the ice giants, got scattered outward. And then eventually their eccentricity and inclinations are damped down by interactions with planetesimals. Okay, so so that's the process where you would imagine that if you have, if this happens on the right time scale, you might be able to tilt Saturn's spin. All right. So, but there is actually again this constraint that you need to change the precession time scale on slow enough. And in fact, Boye, Lascar, and Pachena recently found that if you ask how, the time scale on which you can change G and still stay in the Cassini state, they found that it's actually rapidly, the critical time scale decreases rapidly with increasing inclination. And we kind of confirmed that as a simple experiment. So on the left, you see, again, this plotted of alpha over G and the obliquity. So we started with basically just Saturn on an inclined orbit of 0.1 degree. And you slowly change the precession of the orbit. And you see that if the time scale is like 2 and 1 million year, red and green line, you can actually follow the Cassini state all the way up. But if you go below that, then you see that it would actually drop out of the Cassini state. All right, so if you plot then that minimum time scale as a function of the inclination of the orbit, it goes roughly like 1 over the inclination. So if you're very low inclination, there's a problem because you're now talking about time scale of billions of years, and the characteristics time scale on which the migration happens is on the order of millions of years or maybe 10, 20 million years. Right? So, but then you notice that you go up to about 10 degrees, then you are roughly in the right ballpark. You're now talking about 10 million year time scale. That's the critical time scale. Okay, so, and that's important because during the encounter phase, this is an example I did a while back. During the encounter phase, in fact, the ice giants can get up to 10, 15 degree inclination. So if you stay there long enough, then you could, in fact, have enough time to tilt Saturn's oblique spin. So the first set of simulations we did was do the simple problem where you actually have what's called secular interaction. So we have 4 giant planets. We have imposed migration of the planets on timescale tau. And the planets only interact by secular interactions through Laplace-Lagrange equations. So there are no close encounters in this problem. So you just nicely diverging migration of the planets. And the spin evolved due to torque from the sun. And we vary the ice giants' initial orbital inclinations from 1 to 10 degrees. So here's an example of what you would see if you have 10 million years and the inclination is 10 degrees. Right? So the upper left showing you the semi-major axis and the perihelion and aphelion distances of the 4 planets, orbital inclinations, and these are the obliquities. And those are the color lines are the secular frequencies of the giant planets, and the black lines are the these are the spin frequency, precession frequencies, and these are the secular frequencies for the inclinations. There are 3 of those. All right, so you can see that Jupiter. So this is actually pretty typical. You see that Saturn, in fact, is caught in the resonance, and it goes up to all the way up to 30, 40 degrees in obliquity. But at the same time, when the frequency crosses with Jupiter, you also get an increase in the obliquity of Jupiter. In this case, up to 20 degrees. And that's actually quite typical. And so this is a plot showing you obliquity of Saturn versus Jupiter for all the simulations we did. And the cross is the real solar system. And you see that you typically get both. If you manage to get large Saturn obliquity, you also get large Jupiter obliquity. Okay. All right. So then we move on to do some more realistic simulations. Again, so you have to do a lot of simulations. So we can't really do the whole planets plus planetesimal simulation. So we just do just the 4 giant planets, again with imposed migrations and imposed damping of eccentricity and inclinations. And this is done with a code that I modified a few years ago based on Simba. So the spin can evolve both due to torques from the sun and from planet-planet interactions. Okay, so these are fairly typical examples. So the one on the top is for a short migration time scale. And you see that nothing happened to the spin of Jupiter and Saturn. Although in this case, in fact, there's an encounter between the 2 ice giants. And that caused about 10 degree obliquity for the 2 ice giants. Okay? And then for the lower 2, you see examples where, so these are the more typical examples of different time scale, where there are encounters between, especially between the ice giants. And in this case, you get obliquity about 10 degrees for both Jupiter and Saturn. And this is a case where you get very little obliquity for Saturn and almost 40 degree or 30-some degree for Jupiter. Right? So again, this is more typical of what you see. So again, if you, and this is actually the best case we came up with, where Jupiter, so Saturn, the green one, is about, so the average obliquity is about 15 degree, and Saturn is about 5 degree. Okay, so this is a plot on the left again showing you all the numerical results of obliquity of Saturn versus Jupiter. And you see again this trend that most of the time you get Jupiter's obliquity comparable to Saturn, and actually when you include the interactions between planets, it seems to be scattering on this end, so that you're more often getting things that have actually large Jupiter obliquity instead of compared to Saturn. Okay, so you can actually get obliquity for Saturn that's about 10 degrees, typically if you go up to a time scale of about 15 to 20 million years for the migration time scale. But again, as I said, you then typically ended up with Jupiter obliquity comparable or even larger than Saturn's, which is bad. And in addition, if you're talking about 15 to 20 million year time scale, this is a plot of, so you start with four giant planets, and what's the fraction that actually this is actually ejection fraction. So if you have only 3 or less giant planets left at the end. And you see that if you're talking about 15 to 20 million time scale, you're now talking about less than 20 to 25 to 30% of the system still have 4 planets left at the end. Okay? So since we have only 1 minute, I'll just briefly mention. So this is all in the context of what's called the original Nice model. So we've started doing some work on the version 2 of the Nice model, where they actually put 4 giant planets originally in mean motion resonances before the planetesimal caused the divergent migration. So in this case, there's a little bit more scatter in terms of the obliquity, Saturn versus Jupiter obliquity plot. And we have one case that looks pretty close to the cross, which is again a real system, and this is this case here. But this one is bad because so even though the obliquities are pretty close, this one is one of those that actually almost ejected one life giant. And also, I think we have a little bit of a problem about the description. We haven't quite figured out the correct description about migration and eccentricity damping, because it seems like often we ended up with instability as soon as the system goes out of the mean motion resonance. So we still probably have to play around with this a little bit more for Nice version 2. Okay, so the summary. So it's possible to tilt the spin axis of Saturn by this secular spin orbit resonance due to the divergent migration of the giant planets. But there are 2 problems with this. One is that we more often than not ended up with Jupiter tilting over even more, or at least comparable. And so that's in contrast to the 3 degree that you actually see in the real system. And that if the you can get larger obliquity of Saturn by going to longer migration time scale, but then you have the problem that the survival fraction, having all 4 giant planets surviving is very low. So I'll stop here. Thanks.
I just have a comment. I mean, what the Nice model does is try to come up with an example of evolution that gives rise to something that looks like the present solar system. And of course, you're really working backwards on a very irreversible dynamics to try to do that. Normally, these dampings and so on. You start big eccentricities, they land, the inclinations land, and so on. Now you've added an extra ingredient. So you've asked if we also try to get obliquities correct. Can we fit that into this sort of Nice picture? And you find that trying to match one more thing, really 2 more, I guess, 2 obliquities, it gets really hard. Right?
Yeah.
maybe not so surprising. It always seemed to me that the success of this model was that every time that somebody pointed out that they left something out of the model, they then found some new initial condition which could make something look like the present solar system. But put more constraints on it, it gets still
Well, and I think the question goes back to what else caused the resistance.
So that may be also maybe working backwards these very reversible situations. It's a question.
Any other comments or questions? History of the solar system or anything else? Well, then we'll move on to Wayne, who's going to give the final talk of the session and move us full circle back to the Galaxies. Maybe. We'll see.
So I'm going to talk today about flashing. Extracting structural information from images of spiral galaxies. I'm at UC Irvine, except now I'm on sabbatical at Imperial College right now. Most of the real work, of course, was done by the graduate student here in Davis. I also have a collaborator, Eric Munoz, who's helping me with grammar, so I'll talk about that from a bit of time. And Aaron Barth is the astronomer at UCI, who is keeping me honest when it comes to astronomy. So, first of all, I want to give you a crash course in computer vision. It turns out that computer vision is very hard. It's been about 10 years away for the past 50 years, which is like artificial intelligence. One of the classic problems that people have worked on is the find the tiger problem. So, of course, you can all find the tiger. The problem is try to create an algorithm that will find the tiger robustly. It's not easy, partly because there's lots of possible backgrounds. You can create a trivial algorithm which says if the pixel is green and it's grass, if the pixel is yellow or black, then it's a tiger. That might work well for those images. The problem is it will also work well for this image. I'm going to skip over almost everything in the past 50 years in computer vision and just highlight a few very significant advances that occurred. One of the best ones was in the early 90s, Jeff Hinton, right here at U of T, along with his research group, finally found a way to recognize handwritten digits. And as a matter of fact, the U.S. Postal Service now uses a similar system for their zip code detection. It uses a neural network. Here's a very simple example of a neural network. It has 2 layers. The top layer has 4 nodes. The bottom layer has 6 nodes. The real neural network that was used to solve this the digit recognition problem has 4 layers and 3,000 nodes. So I won't try to plot here. It uses what's called a generative model. In other words, it can stochastically generate images that look like handwritten digits and then compare those to the real handwritten ones. And remember, this generative models will come back to haunt us later on in the talk. Another relatively major advance is the find the hippo problem. And the find the hippo problem is a bit harder than the find the tiger problem, because tigers are yellow on a green background, hippos are brown on a brown background, so it's a bit harder. Everything's brown. The algorithm that solved this was called blob world segmentation. And the idea is that every single pixel has assigned to it a state machine, and that state machine iterates and tries to figure out which one of my neighboring pixels do I want to associate with. And you can see here with this algorithm automatically does a relatively good job of separating the water from the hippo, and it even managed to separate the hippo's reflection. It does not successfully separate the hippo from its shadow. You can see that's all one big blob. And the other big thing to recognize here is that it's not really detecting a hippo, it's just detecting blobs. This algorithm would not be able to distinguish a hippo from a brown rock, okay? And what we would really like someday is to have commander data, right? We want to hold a picture of New York's Central Park to an algorithm, and in that picture there's going to be clouds and trees and sky and a jogger and some grass and some tree trunks and a car and a dog and a fence and who knows what else. And the algorithm should be able to correctly identify all those things just like any of us could, truly. People are working on such algorithms, and here's how they do when given a standard picture of a find a tiger. They can find some grass, they can find some more grass, they can find a cat, not bad, they can find a tiger, good, but they also find buildings, horses, and bears. So we're a long way off from commander data. This looks trivial. Why is it such a hard problem? You have to remember that you have an unfair advantage over the computer, and that is there's a couple 100 million years of evolution that says if you can't find the tiger will find you, and you will become tiger food. Okay, so there's a strong evolutionary pressure for all of us to be able to take off our glasses, look at the world, and actually understand what we see. So about 25% of your brain is devoted to vision, and like it or not, the human brain is still by far the most powerful or most sophisticated computer on the planet, and 25% of a human brain is a lot of compute power, okay? Why am I harping on all of this, despite the fact that it has nothing at all to do with astronomy? I just want to emphasize to you that the results I'm about to show you, they really look trivial. But it's a hard problem, simply because vision is a very hard problem to solve, and I want to impress upon you the mind-boggling amount of pain and suffering that computer vision people go through in order to solve things that you can do with a casual glance. Let's move on to the astronomy now. What kind of data sets might we want to apply galaxy image recognition to? The Sloan survey already exists, has about 1 million galaxy. The LSST is being built right now in Chile. It'll map the entire sky repeatedly and gives about 30 terabytes every single night. The Joint Dark Energy mission hasn't been funded yet. It's the next incarnation of what was SNAP. It's a proposed orbiting mission that will repeatedly map the entire sky, well, large portions of the entire sky from orbit at a resolution comparable to HST. So what's that thing going to see? Well, on the next slide, I'm going to show you the Hubble All-Deep Field. It was taken in 2004. And it's what you see if you take the Hubble Space Telescope, find the darkest patch of absolutely nothing that you can find in the sky, and point the telescope there for 12 days. What do you see? Well, this is what you see. You see a bunch of galaxies from the very early universe. You see some spiral and lots of irregulars. Not very many ellipticals, because there hasn't been enough time for mergers to occur and form lots of ellipticals. There's a few there, but no big ones. So that previous image contains about 10,000 galaxies from the very early universe. It comprises 1/13 millionth of the entire sky, or 1/50th the size of the full moon. So do the math. 13 million times 10,000. There's about 10 to the 11th galaxies visible at HST resolution over the entire sky. And this is what the Joint Dark Energy mission will see, except multiplied by 13 million. So there's lots of shape to be understood in the sky, but nobody even tries to predict simple things like arm counts or other shape information from copious amounts of n-body simulations that everyone loves to do. Why aren't we looking at millions of galaxy shapes in the sky and comparing them to millions of galaxy shapes that we can find in simulation? You already know the answer. I already told you at the beginning of my talk. The answer is because computer vision is a hard problem. So there's no point in making any predictions because there's no hard data to test the predictions, even statistically. Turns out that vision is easy for us because you can't find the tiger will find you. On the next slide, I'm going to show you, to demonstrate this, I'm going to show you two images, two galaxies. One of them has lots of arms, the other has not very many arms. I want you to figure out which one is which, and I'll give you 1 second to do it. Ready? Time's up. Okay, so how many of you thought the left galaxy had more arms? How many of you thought the right galaxy had more arms? Excellent, great. You're all hired into my new NSF-funded program. Millions of dollars you're going to spend the rest of your life classifying galaxies just to me. Thank you very much. Actually, that won't be funded because it already exists. It's called the Galaxy Zoo. It's a website where you and your 12-year-old kids can go and classify galaxies for astronomers. Galaxies for the rest of your life with, spiral, non-spiral, lines left, lines right, 2 arms, 5 arms, big balls, small balls. The problem is that 150,000 12-year-olds isn't enough for 10 to 11 galaxies. Many people can see 500,000 galaxies for a 12-year-old. 12-year-olds might get bored by that point. And furthermore, 12-year-olds are not good at objective quantitative measurement. Ask them to count the arms, fine. Ask them to measure pitch angles, no. They're going to go back to video games. So we need something that can do this automatically. What sort of questions might we ask or try to answer? Actually, I don't know. That's why I'm here to ask you guys. I'm just a computer scientist who likes to play with astronomy problems, but here's my take on what kind of questions we might want to ask if we could parse images of spiral galaxies. What fraction of galaxies are spiral versus elliptical versus irregular? Maybe you guys already know that. In spirals, how many arms are there? How thick are they? What are the pitch angles? What are the brightness profiles? Is there clumpiness? Where is the clumpiness? How big is it? How much gas? How much dust? And where is it? How do these numbers change as the universe ages? Just from a couple of talks this morning, ideas, I got some statistical corrections in weak lensing for non-circular shapes, although my cousin shot that down when I suggested it. Barbara Ryden's talk also suggested that spiral galaxies form with opposite spins. Well, we can check that with edge-on spirals using redshifts, but for face-on spirals, you need some kind of vision algorithm to tell you this galaxy winds one way and the other galaxy winds the other way. A really simple question we'd like to answer: does the universe have total angular momentum 0? I would guess that the answer to that question has enormous consequences for the early cosmos. When the universe was this big, it was spinning. It probably has some cosmological implications. If we can look at all the galaxies in the universe and count the number of spirals rotating clockwise versus anti-clockwise, we can answer that question. Except the only way we can answer that question right now is with an army of 12-year-olds. There do exist some algorithms to perform spiral galaxy fitting. One of them is called GalFit, written by Chen Ping and Victoria. Here's M51. Here's Chen Ping's model of M51 in GalFit. The problem with GalFit is it's not automated at all. My colleague Aaron Barth at UCI says that if he were to try to generate this fit of M51, it would take him hours or even days. This was actually done by Chen Ping, who's kind of cheating. He's the author of the program, so he might have done it quickly. But the point is, it's not automated, so it's no good for 10 and 11th galaxies. Oh, and also, if GalFit doesn't like your parameters, it gives you an ASCII mushroom lab. So, computer vision consists basically of a huge bag of tricks, and the finesse is basically boils down to knowing which trick from that bag should you use. One of the tricks that we use is a language developed at UCI. So I need to describe to you what a grammar is. So here's a one-slide crash course in a grammar. Grammars are examples of things that can parse things and define things. This is a very simple grammar. It defines a string. The string can have one of two forms. It's a string S. It's either nothing, it's the empty string, or it's a string that starts with an A, ends with a B, and has a similarly defined string in the middle. Not too much thought should make you recognize that this grammar defines or only allows strings of the form a bunch of A's followed by exactly the same number of B's. Okay? The act of deciding whether a particular string satisfies a particular grammar is called parsing. This is what your compilers do when you're compiling your favorite C, Java, or Fortran program. The opposite of parsing is called generation. We can follow the grammar rules backwards and basically, choose at random which. Large grammars have many more production rules here, but you can choose at random which grammar rule to follow, and you can randomly generate syntactically correct strings at random. That's how some of my computer science students actually do their programming assignments. Sometimes that's what I wonder. So that's what a grammar is. We have a language at UCI called Plenum, which is a vastly more powerful grammar that allows you to define pretty much anything you want. Anything you want to simulate at all can be defined in Plenum. For example, we can generate model galaxies the following way. This is a very simple grammar. A spiral galaxy, so this is generation of pictures of galaxies. I'm not claiming this is how galaxies actually form. Okay? This is just generating pictures of galaxies. A spiral galaxy at position X consists of a bulge at position X and a rule called an arm generator, which starts at position X, with probability 1. So all galaxies have these two things in them. I should specify beforehand that this grammar here generates very, very simple galaxies, which just are pairs of arms emanating from the center. An arm generator at position X generates two arms, starting at initial angle theta 0 and theta 0 plus pi, so two arms just coming out of the center of the galaxy in opposite directions. Both arms start at position X, and they have initial lengths of 0 and 0. And there's some random numbers in there. A particular arm at position X, currently at angle theta and currently of length r, solves the differential equation where the length is growing with some with some constant value, and the angle is also changing at some constant value. So it's just a couple of lines coming out of the core and winding around. And the arms stop probabilistically, so they have a length which is stochastic. Okay? Now again, this time variable is not time in the sense of galaxy evolving. It's just a parameter defining a model. So this is a very simple model. We can generate more complicated models of galaxies looking like these. The grammars are much more complicated, so I'm not going to show them to you. This here is an actual example of us trying to fit a grammar-generated galaxy to a real image. So here's a galaxy with two arms. The blue and the green lines here represent a random initial condition for a model galaxy, and we perform what's called an expectation maximization. It's a very standard algorithm in machine learning, but don't worry about it. And after fitting, we can actually do a reasonable job of classifying the pixels according to which arm they should be in. Okay? The problem is that not all galaxies look this clean. I'll say that grammars are very, very powerful. They can model almost anything, but it's just too expensive to fit complex models to grammar, so we end up we have to use kind of ad hoc methods, which is what I'll talk about for the next few minutes. As I said, computer vision is a bag of tricks. One of the tricks is called a Huck transform. A Huck transform is just a fancy way, an efficient way to find straight lines in an image. Okay? How it works, don't worry about it, but it can find straight lines. So how can we use that? Well, we can take the image of a galaxy, and we have an algorithm. You guys already also have an algorithm that can find the center automatically of the galaxy. We're going to look at the galaxy in polar coordinates, so the r theta space, but we're going to plot the polar coordinates in our Cartesian frame, right? So this galaxy looks just like this once you transform from polar coordinates and view those polar coordinates in a Cartesian frame. And voila, spiral arms look almost like straight lines, and the Huck transform can find those straight lines. And from that, we can get the winding direction of the galaxy and the pitch angle more than 90% of the time we get it right. Another trick we use is called orientation fields. This was by Kim et al. A while ago. The idea here of generating an orientation field is you slap down a bunch of vertical lines vertical black lines on the image, and that will find for you the areas of the image that are aligned vertically. And you do the same thing with a bunch of horizontal lines that can find the horizontally aligned or oriented parts of the image, and that's the orientation field that we get here. And we can now cluster pixels. If every pixel has an orientation, we can now cluster the pixels according to their orientation and actually pull out arm segments. Okay, so now we are clustering pixels according to orientation, not brightness, but orientation. And once we have these clusters, we can perform a fit of a logarithmic spiral to each of the clusters. And with that, we can then, let me just show you a very quick sequence of frames. So here's a picture of a galaxy. Here's a contrast-enhanced version of that galaxy. Here is the clustering and the arm fitting that we get. I'll just flip back and forth quickly between the original, between the contrast-enhanced, and you can see that we're pulling out clusters, and this is what the lines look like when put on the original galaxy. Here's the galaxy, contrast-enhanced, the clusters that we found, and here's the lines. So we have 8 of those. I won't go through them all now since I'm getting a big hint from this gentleman here. And here's my slides now. I don't know why some got screwed up. But anyway, so here there are 8 galaxies here, but 2 of them have vanished. Here's some example results. And what I would like to hear from you guys, since I'm not a real astronomer, is what other sorts of information would you like to see extracted from these sorts of images? Thank you.
Sometimes human vision doesn't notice the 5-minute remaining song.
It wasn't in this, I was sharing
Any questions or instructions for Wayne? Since Stacey's here, we are missing him to be coffee break, so we really have time for
You
questions.
must realize how far ahead you are relative to them, so we're grading people that are you're doing a good job.
The speaker is getting it out. So yeah, questions or comments?
So you're finding all these arms using a Hodge transform, or
No. We're using a clustering algorithm based on the orientation field. The orientation field we get from plotting down lines and getting orientation for each pixel. Each pixel has an orientation.
how does that pixel have orientation? Right.
So this is how we get the orientation field. So if you slap down a bunch of vertical black lines here, then you can find the parts of the image that are kind of oriented vertically by looking for vertical lines. The same thing with say you have a bunch of black horizontal lines. That gives you each part of the image has some like right here. This is a a part of the picture that's oriented vertically. Here's a part of the picture that's oriented horizontally. That gives us for each pixel an orientation. Not a vector field. There's no direction. It's just horizontal, vertical, diagonal. And once we have an orientation field for each pixel, then we cluster those pixels according to orientation. And that's what this is showing here. Right? We have all of adjacent pixels along this arm have similar orientations, and we cluster them hierarchically. And that's how we pull out these arm segments. Okay.
You mentioned all the drawbacks and difficulties of your field, but what are the real successes? What are the algorithms that you
Well, I pointed out just a couple of examples, right? There's the handwritten digit recognition, which was a big success, and this blobbing algorithm where it's a very expensive algorithm that you assign a state machine to each pixel, and basically pixels decide who their neighbors want to be. That's called blob world segmentation. That's one of the first successful algorithms that can find pixels that are related to each other in an image, although they can't tell you what they are, whether it's a hippo or a brown rock, they can't tell you. But they have generally they're successful at that, blobbing together regions of pictures that are related to each other. That's as far as computer vision has gotten, really. It's really, it's almost incomprehensible how difficult the problem is, considering that we can do it with a quarter-second glance.
Great. All right. Well, it's been a great session. You might as well get the first dibs on the coffee.